Virtual reality, immersed in high-performance computing and communications. This is jacking into cyberspace. But it's really happening like this in California, Florida, Illinois, Colorado, Connecticut, Alabama, Washington, and Virginia, in Germany and Japan. And people are seeing and touching and manipulating and changing their data like this in Chicago, Washington, D.C., Yorktown Heights, Pittsburgh, Boston, and Silicon Valley. They are immersing themselves in science in Champaign-Urbana, Madison, Argonne, and Chapel Hill, in manufacturing and construction at NASA Huntsville, NASA Ames, Marietta, Georgia, and Peoria, Illinois, in healthcare in Chapel Hill, Rockville, Hanover, Princeton, and Chicago, in education and lifelong learning in Seattle, Pittsburgh, and Washington, D.C. Suddenly, we are no longer outside the computer looking in, but we are inside the computer looking out. This is immersion. This is virtual reality. Virtual reality is the product of 3 decades of advances in display technology and high-end computing. Early computer graphics were a natural outgrowth of radar. In the 60s, computer-aided design first appeared. By the late 60s, primitive virtual reality was operating in real time. By the 70s, flight simulators could present dynamic, although visually simple, real-time scenes. Early supercomputers were used to further research in visual realism. Unlike the real-time flight simulators, these animations took minutes or hours per frame to compute. By the early 80s, the flight simulators achieved better realism through advanced hardware, software, and motion control platforms. At the same time, and throughout the 80s, the quest for realism bore fruit. Some of these exquisite images took an hour per frame to compute, which is 100,000 times slower than real time. Interactivity and pleasing realism came together on workstations by the late 80s. In the early 90s, immersion in the display was achieved by bringing the screens closer to the eyes, or making the screens much, much bigger. Adding textures, shadows, and smooth motion adds to the effect. Being immersed is suddenly quite believable, and it can be breathtaking. Current research in virtual reality is applied to science and engineering, manufacturing, healthcare, and education and lifelong learning. The National Center for Atmospheric Research has developed a prototype virtual reality system for landing in bad weather. Clouds are not a problem to pilots given modern guidance systems, except that clouds may obscure severe weather problems like microbursts, which cause crashes. Based on real-time radar data, this system strips away the clouds and clearly shows the hazard with time to spare. At the University of North Carolina at Chapel Hill, virtual reality is being explored for use in radiation therapy planning. The physician examines positions of multiple radiation beams for cancer treatment. Where the beams cross, the effect is optimal. Here, virtual reality aims to give 3D verification that the placement is correct and that no healthy tissue is harmed. The physician can look all around and even enter into the patient's organs to see the beams crossing. In the manufacturing sector, building and testing prototypes is an essential but extremely expensive and time-consuming part of the design cycle. Virtual reality at the National Center for Supercomputing Applications at the University of Illinois at Urbana-Champaign is helping Caterpillar engineers see out of their loaders before they are built. Changes can be made to the CAD drawings and quickly retested for visibility, thus shortening the design cycle. At Argonne National Laboratory, researchers are developing ways of visualizing the molecular mechanisms of cancer. Data from supercomputer runs simulating protein action can be viewed using the CAVE Virtual Reality Theater at the University of Illinois at Chicago. While computing on the Intel Delta, Caltech scientists collaborate with colleagues in Chicago across the internet, viewing the simulated firing of neurons in the brain. University of Minnesota researchers fly through a simulation of the Kuwaiti oil fire smoke plumes drifting downwind through the Persian Gulf. And astrophysicists from the National Center for Supercomputing Applications study the birth of the universe and the formation of the galaxies. NASA Ames Research Center has pioneered virtual reality research and applications in flow-field visualization for nearly a decade. Here, the operator is using the boom to look into and steer the real-time supercomputer simulation of particle traces. NASA Ames telepresence research puts you there. Your head and hands operate a remote imaging and sampling vehicle underwater in Antarctica or on another planet. This type of virtual reality puts you inside a robot, with you in control. Virtual reality is a field in which entrepreneurial individuals can make major contributions. Myron Kruger showed his first artificial reality and telepresence concepts over 20 years ago. Here, no data gloves are required. Gesture recognition uses hand motions as input to control critters, colors, and action. At Boeing in Huntsville, Alabama, models of the space station Freedom are explored to test maintenance and operation plans and train astronauts before the physical prototypes are built. Virtual reality is also used to design factory machine layouts and production flow, and to demonstrate compliance with standards and safety regulations. Children in Seattle at the Human Interface Technology Laboratory design their own worlds and test them out. Virtual reality, although expensive now, will enter homes and schools in video game hardware. It is up to our educators and publishers to provide the instructional content and realize the potential of this compelling medium. Many near-term virtual reality opportunities will be in entertainment. Sophisticated input devices, like the one shown here controlling real-time animation of Mario, in conjunction with consumer virtual reality gear, will help spawn industries. Virtuality Systems provides a very popular multiple-player virtual reality game in arcades. Dactyl Nightmare literally carries you away. Experience virtual bobsled training, play an instrument, or conduct an entire orchestra. Entertainment is the international strategic market which will likely drive the personal computer industry this decade and next. The High Performance Computing and Communications Initiative is developing computing, communications, and software technologies for the 21st century. These technologies will tightly couple with the growth of the virtual reality industry and its applications. The National Information Infrastructure will encourage and enable our access to high-performance computing and communications. Virtual reality provides a high-end test bed for matching state-of-the-art computers and high-speed networks to humans, one, several, or even thousands at a time. These scientific and engineering visualizations are the future of virtual reality, not the present. These animations require computing speeds many thousands of times faster than possible on today's workstations. If a simulation now takes an hour per frame to generate, by the late 90s, the teraflop parallel computer will compute it in real time, in virtual reality. Is this 100,000 increase in computing desirable? You be the judge. Chemical and biological catalysts are involved in 25% of the gross national product. Real-time investigation of catalysis could drastically improve the time to market. Weather is real-time, yet today's computational simulations of severe storms take many hours of computer time. Getting inside the storms to release tracers is a research goal of scientists working with virtual reality. Better understanding and prediction of the weather can save billions of dollars. The ways pollution moves through our air and water and the ways pollutants interact with each other are just now being modeled on supercomputers. Virtual reality can take students and researchers from the molecular level to a global view while playing what-if games. This animated walkthrough of the River Bend nuclear plant shows the kind of detail which will soon be common in virtual reality systems tied to high-performance computing and communications. Healthcare delivery can be improved through virtual reality and telepresence so that specialists may remotely access a patient. High-speed networking is a must. A volume visualization sent fast enough to achieve virtual reality needs thousands of times the data throughput of email, the difference between copper phone lines and optical fiber networks. What is it worth to thwart a terrorist attack with the potential of leveling Manhattan? Virtual reality augmented missions will require fine-grained geopositioning capability, accurate models of terrain, streets and buildings, motion effects and sound, all in a shared workspace. Warbreaker, a nationwide network of defense simulations, ties command and control centers to aircraft trainers to provide mission planning and battle preparation. Military advances represent dual-use technology. Transfer to civilian fire and police departments is certain. It's now a question of maintaining technological superiority, understanding our environment, managing energy, recreating education for the 21st century, providing quality health care at lower cost, and just plain being competitive in a global economy. It's time to immerse ourselves in high-performance computing and communications.
The Cave Virtual Reality Theater is a projection-based system. The illusion of immersion is created by projecting stereoscopic computer graphics into a 10-foot cube made of screens that completely surround the viewer. Viewers explore virtual environments by walking in the cave space. Head and hand tracking systems produce the correct perspective projection from the user's point of view and determine the position and orientation of a handheld device we call the wand. This device is used for control and interaction with the virtual world. An audio system is also used and provides sound feedback. The current implementation of the cave has 4 screens, 3 surrounding walls, and a floor. Each side of the cube has an associated Electro-Home projector and a Crimson Reality Engine workstation from Silicon Graphics. Mirrors are used to fold the optics to reduce the space required between the projectors and screens. Stereographics LCD shutter glasses provide stereo viewing. The tracking systems are a Polimas IsoTrack and Ascension Technologies Flock of Birds. The audio system includes a sampler with a MIDI interface and 6 speakers. The entire cave system is controlled by a Silicon Graphics Personal Iris. The cave is a non-intrusive interface where reality and virtual reality are combined naturally. Wearing lightweight LCD shutter glasses, users can see themselves and their real surroundings blended with the virtual environment. Interaction with the virtual environment is done with the wand. Its controls and functions depend on the needs of each particular application. In this application, we can see how it is used as a navigation device. In this one, the wand maps the user's head with the computer-generated head. As the user slices his head with the wand, he can see the different sections of the internal structure. Another use for the wand is the ability to pick and move virtual objects. Audio feedback is used to complement the illusion of immersion. Visuals and audio are choreographed to respond to the user's actions or to reflect the state of the virtual environment. Multiple users can easily share the virtual experience by putting on a set of stereo glasses and stepping into the cave. In the current implementation, one user actively controls the viewpoint by wearing the tracking glasses. Other users passively perceive the experience, much like watching a 3D movie. Since the cave gear is so easy to wear, users frequently exchange the tracking glasses during the experience. This shared experience also allows for guided tours by an expert navigator. The cave is a general virtual reality interface. Its design is flexible enough to be used in a variety of applications. Most applications shown in this tape are collaborations between the Electronic Visualization Laboratory and invited researchers from various disciplines. The cave is an effective visualization tool which provides scientists a new way to explore their research data.
At the Electronic Visualization Lab, graduate students worked with scientists to use the CAVE virtual reality theater to visualize their research data. Most of these applications are experiments or demonstrations to apply virtual reality techniques to computational science. In brief, the CAVE is a projection-based system. The illusion of immersion is created by projecting stereoscopic computer graphics into a cube composed of display screens that completely surround the viewer. A sound system provides audio feedback. The viewer explores the virtual world by moving around inside the cube and manipulating objects with a wand-like device. Here we present an overview of the results of their collaborations. This is a graphical representation of a model for superconductors. The goal of this visualization is to evaluate the use of virtual reality techniques in superconductor research. We use the technique of successive refinement to display the replicating structure of the superconductor. This application is a visualization of brain activity resulting from a visual stimulus. The voltage potentials are mapped onto a color scale and superimposed on a head model. Musical instruments are assigned to the different electrodes used for the recording of EECG data. The resulting audio patterns are associated with specific brain configurations. The Cosmic Explorer uses the cave for exploring the stages of the evolution of the universe since the Big Bang. Each one of these points represents an entire galaxy. Viewers can explore interesting galaxy configurations by simply walking to them. A tool to fly through the universe is also provided. The climate over the western region of North America and part of the Pacific Ocean is simulated in this application. Viewers explore the landscape, temperatures, winds, water vapor, and several other climate elements. This application is a visualization of a job executing on 128 processors of an Intel Touchstone Delta parallel supercomputer. The 128 processor array is arranged in a grid centered in the cave. Arrows illustrate the interprocessor communication. Each slice represents a time step on the delta. The flight of a virtual airplane over the city of Chicago is an example of an architectural walkthrough. In autopilot mode, users can relax and enjoy the flight. For more adventurous viewers, the wand is used as a navigation interface over the city. In this piece, we are visualizing the behavior of piezoelectric crystals. These crystals are important components in electronic appliances such as computers and cellular phones. We use a virtual blowtorch to simulate the application of heat to the crystal. The crystal expands in response to heat and contracts when the blowtorch is turned off. We also simulate an electrical probe for electrical stimulation. Now let's take a more detailed look at a few of these applications. The purpose of the Fractal Explorer is to investigate the structure of mathematical objects. In the cave, viewers are provided with tools to manipulate the equations that generate the fractal objects. The tool we see here is a ribbon that is anchored at the tip of the wand with its tail free to flow into the Lorentz attractor. The viewer can explore the attractor's shape by moving the wand around its field and observing the movement of the ribbon. Another tool is a virtual sphere which surrounds the attractor, allowing the user to rotate it for a better view. The development of these tools was very natural in the cave, where viewers can naturally move around the data and manipulate the control device in 3 dimensions. Molecular dynamics simulations are used here to observe the behavior of the P21 protein. The P21 molecule regulates cell growth by interacting with another molecule called GTP. The P21 protein is particularly relevant because changes in its molecular structure can lead to uncontrolled cellular growth and cancer. Viewers can observe the molecules by walking around or into them. Also, the molecules can be grabbed and manipulated with the wand. Initially, the base chain of the molecule, called the alpha carbon chain, is presented to viewers. The wand is used to display the molecular structure in full detail. Water molecules acting in the vicinity of the P21 molecule can also be observed. Sound is used to provide feedback. This demonstration provides a starting point for a more elaborate immersive environment for the study of the P21 dynamics. The interaction between 2 neurons in the cerebellum, the Purkinje and inferior olivary neuron, are shown here. The wand can be used to initiate an action potential in the olivary neuron that triggers a complex spike event in the Purkinje cell. A color scale is superimposed over the neurons to visualize the activity. This environment offers neuroscientists the first fully immersive visualization of the interaction of the 2 neurons. In this application, the cave is used to illustrate a theory of how the cholera toxin infects a healthy organism. The cholera toxin is represented by 2 components, a red donut-shaped unit and a smaller yellow drop-shaped unit. The cell membrane and the cholera toxin docking place are represented in blue. The cholera infection can be observed as the toxin passes through the cell membrane. Scientists have reported that this application provides a new way to study the dynamics of cholera infection.